Hello friends, welcome to the lecture. In today's lecture we will discuss some basic concept which is very useful in further further lectures. So let us start. Differential equations are used to express many general laws of nature and have many applications in physical, biological, social, economical and other dynamical systems. In particular, the origin of differential equation may be considered as the effort of Newton to illustrate the motion of particles. This is a very famous example, and these equations may provide many useful information about the system if the equation were formed incorporating the various important factors of the system. So, here if we consider let y equal to f t be a given function of independent variable t, then the change in y with respect to t can be represented as the derivative dy by dt. So, in many real world process, the variable representing the important factor of the process and their rate of change are related to each other in terms of some basic principle of the process, which most of the times the representation of these relations in terms of mathematical forms turns out to be a differential equation, and in this way we can explain the vital utility of the differential equation in most of the dynamical system of the modern science and technology. So, let us start with the definition, proper definition along with some examples. So, as the name indicate, a differential equation is a relation between independent variables, dependent variables and its first or higher order derivatives. So, for example, if independent variable is t, dependent variable is y, it means that y is a function of t, and we can consider the first or higher derivative, it means that y dash t, y double dash t and so on. So, any relation which relate t, y, y dash t, y double dash t and so on is considered to be a differential equation. Now, depending on the number of independent variable, we may classify the differential equation in two parts, ordinary differential equation and partial differential equation. So, in ordinary differential equation there is only one independent variable. So, let f t define a function of t on an interval I. Here I is open interval a to b, and by an ordinary differential equation we define an equation involving t, f t and its one or more higher derivatives. So, here are some example of ordinary differential equation. If you look at this first one is dy by dt equal to alpha y. Here alpha is any real constant which is a positive, and d2y by dt square as g. This is second example, and third example is dy by dt equal to 3y square sin t plus y, and fourth example of differential equation is m d2y by dt square equal to mg minus alpha dy by dt. If you look at the first example, here y is the dependent variable and t is the independent variable, and dy by dt is the first derivative of y with respect to t, and it is related to the variable y, dependent variable y, by this relation dy by dt equal to alpha y. This is a very commonly used equation in population dynamics, and it says that if the population say grows with the rate of alpha, then the population at any given time t can be obtained with the help of this differential equation. And if you look at the second equation d2y by dt square equal to g, basically this is what when you consider a particle say falling from a particular point, then this will represent the equation governing the motion of that particle, and it is given as d2y by dt square equal to g. Here this g represent the gravitational force, and this is third one is dy by dt equal to 3y square sin t plus y. Here this represent a particular say motion of some particle, and in 4 if you look at m d2y by dt square equal to mg minus alpha dy by dt, and if you look at this is similar to equation number 2. In fact, in equation number 2 we have ignored that there is any kind of friction due to air on this particle. So, here we are assuming that this particle is moving under only the influence of gravitational force, and there is no other say restriction on that particle is put. Now, but if we assume that this air, if this air put some kind of force upward, then we can modify the equation number 2 in this way. Here this alpha dy by dt represent the friction due to air. So, here this second can be modified in this way. Here we can write m d2y by dt square equal to mg minus alpha dy by dt. Here alpha represent the constant which says that the restriction or the force due to air is proportional to the velocity of the particle. So, if we assume alpha is 0, then this fourth equation is nothing but the second equation. So, these are some example of ordinary differential equation which we most of the time we came across to solving these equations. So, once we have the definition and the example of differential equation, let us discuss more basic thing about the differential equation. So, first thing is the order of a differential equation. So, the order of a differential equation is the order of the highest order derivative present in the equation. For example, if you look at here in first equation, the order of the highest order derivative is 1. Here we have only one derivative, and that is dy by dt equal to alpha y. So, here we have only one derivative and the order is 1. So, equation 1 is the differential equation of order 1. If you look at the second equation, d2y by dt square equal to g. So, here we have only one derivative and that is of highest order. So, here the order of this differential equation 2 is 2, this 2. And similarly, the equation number 3 is a differential equation of order 1, and in 4 we have two terms of derivative exist. First one is dy by dt and another one in d2y by dt square. But if you look at, this is first order and this is the second order. So, highest order is 2. So, we can say that this differential equation is of second order. And as we have pointed out, this equation 1 represents a very basic population model where a population is growing with the rate of alpha. And equation 2 represents an equation of a particle of mass m falling freely under gravity, while equation 4 may represent the same model, but now with the presence of air which exert an opposite force proportional to the velocity of the particle, that we have already seen. Now, moving on next. So, now we define what is partial differential equation. We have seen that the number of independent variable simply classify the differential equation into two parts. One is ordinary differential equation and another one is partial differential equation. In ordinary differential equation, we have seen that independent variable is only one. So, there is only one independent variable and we are considering all the functions of that independent variable. So, but in partial differential equation we may have, so in partial differential equation there is more than one independent variable, and so the derivative of dependent variable with respect to these independent variables are partial derivative rather than the ordinary derivative. So, here since number of independent variables are more, so if we consider any function of these independent variables, then if you consider the derivatives, then it is coming out to be partial derivative rather than the ordinary derivative. So, that is why we call the equation which involve the function, independent variables and the derivative of function with respect to these independent variable as partial differential equation rather than ordinary differential equation. So, let us consider this example. This let u t x y be a function of time t. This is a time variable and two rectangular coordinates of a point in a space x and y. So, here x and y are space variable and t is a time variable. So, here let consider u is a function of t, x and y, where t is a time variable and x and y are space variable. So, let u t x y be a function of time t. let utxy be a function of time t and the two rectangular coordinates of a point in a space x and y. Then consider the following three equation. First equation is dou to u by dou x square plus dou to u by dou y square equal to 0. So, this is the relation where unknown function u is a function of x and y, and there is no partial derivative of u present in terms of t, and so it is a partial differential equation. It is an example of a partial differential equation. Now consider the second example where all these partial derivative present. So here this is k times dou to u by dou x square plus dou to u by dou y square equal to dou u by dou t, and third one is k times dou to u by dou x square plus dou to u by dou y square equal to dou to u by dou t square. In these last two problems, this k is a constant, and depending on this problem, this k may have some values, and these are very famous examples of partial differential equation. So, the above three equations are classical problems in partial differential equation and are widely used in application. So, equation 1, 2, 3, these equations 1, 2, 3 given in 1, 2, 3 are classical in nature and widely used in problems of fluid dynamics, theoretical physics and many other related fields. And these equations are known as, the first equation is known as Laplace equation, the second one is heat equation, and third one is wave equation. So, this is given here, Laplace equation, two-dimensional heat equation, space variables are 2. So, this dimension is depending on the space dimension. So, here we have two space coordinates x and y. So, it is two dimension heat equation. Similarly, this is two dimension wave equation. Now, coming back to differential equation. So, what we try to do here, first we discuss the ordinary differential equation, we discuss all basic concept, existing uniqueness and related problems in ordinary differential equation, and then we will start with partial differential equation also. So, first let us start with ordinary differential equation. So, an ordinary differential equation of nth order is defined as follows. Here f is some function, smooth function, and it is a function of t, y and yn. Here t is an independent variable, as we have already pointed out that ordinary differential equation contains only one independent variable. So, here y is a function of this independent variable t. So, f is a relation between t, y and yn. Here yn represent the nth derivative of y with respect to t. So, here we can say that here yi, where I is from 1 to n, represent the ith derivative of the unknown function y, and here f is defined in some subset of R n plus 2 and provide a relation between the n plus 2 variables. What are n plus 2 variables? T, y, y dash, y double dash and yn. And but this is the general definition of ordinary differential equation of nth order, but because of the implicit nature of this function f, this may represent more than one differential equation, or we can say that it is it may represent the collection of differential equation rather than a single differential equation. Let us explore this possibility. Consider this differential equation y dash q minus 3t square y dash square plus 3y y dash equal to 0. If you look at, this is a relation between what? Here t is present, y dash is there, y is there, and yes. So, here this is the relation between t, y and y dash. So, it is a differential equation of order 1. But if you look at closely, then it gives not only one differential equation, but it is giving basically three differential equation at once. So, it is given in the form 1, but it represents a combination of more than one ordinary differential equation. If you can solve this, let us right now this is given in a very nice form and we can solve it. So, here we can solve it y dash cube minus 3t square y dash square plus y dash equal to 0. So here if you look at, in all the terms your y dash is there, here y dash is there, here y dash is there, here y dash. So what we can do, we can take out this y dash out, and if you take y dash out, then first term is y dash is, square minus 3 to square y dash plus 3y. Now here y dash, and if you look at in the bracket, we have a quadratic equation in terms of y dash. So we can solve using the theory of quadratic equation, and we can write this as y dash equal to 0 or y dash equal to 3t square plus minus under root 9t to power 4 minus 12y divided by 2. So if you look at this represent one differential equation, and this is the say basically two differential equation. So here we have this differential equation is not only one differential equation, but it is giving you the possibility of three differential equation. So in order to avoid this ambiguity, we assume that given ordinary differential equation is solvable in terms of the highest order derivative. So rather than considering the implicit nature, like here this is the implicit nature. So here we do not know that we are considering only one differential equation or a collection of differential equations. So to avoid this possibility, what we try to what we assume that this yn is solvable. We can solve this equation in terms of yn, and we can write our equation in this form yn equal to g t y up to yn minus 1. Here g is some kind of function given in terms of n plus 1 variable, that is dy y dash up to yn minus 1, and this form is known as normal form or canonical form. So now onward, whenever we try to discuss, we assume that our differential equation given in terms of normal form or canonical form. Actually this will avoid that the possibility of that multiple differential equation considered at one time. Okay. Now coming out to basic concepts, once we define what is a differential equation, we need to define what is solution of differential equation. Similarly, we can define the solution of this differential equation in the following manner. So a function phi t is called a solution of 2 means this equation yn equal to g t y up to yn minus 1 if it satisfy the following condition. Here we need to consider that this t is belonging to at least some interval. Right now I am considering this as an open interval a b. So if it satisfies the following condition, first condition is that phi t is defined and it is n times differentiable on I, so that all these terms exist, y to this nth derivative of y exist and all the given derivative exist, right. And second is that this phi t satisfy the equation 2 for each t in I. So it means that it is not only all the derivative exists, but also satisfy this equation for all t in that particular interval. Then in this case we say that the function phi t is a solution of the differential equation. If any of these two fail, then we cannot say that phi t is a solution of equation 2. Now in this particular course, the aim of the study of the ordinary differential equation is to find the unknown function represented in an explicit form. So our first important aim is to find the solution. Solution means dependent variable in terms of t in explicit form. It means that your phi t is given in terms of t in elementary form, or we can say that in terms of elementary functions. Elementary functions are like for example polynomials, trigonometry functions, exponential function, all combinations of these elementary functions. And if you are not able to find out the solution in explicit form, then we try to find the solution in terms of implicit form, or we need to go further to study the behavior of a solution by available analytical methods. So suppose we are not able to find out the solution in explicit form, means your y is given in terms of some function of t If we are not able to find out that, then we try to find out a relation between t and y, and in terms of like ft yt kind of thing, and it is known as implicit form. But suppose we are not able to find in these kind of explicit form, we try to find out the behavior of the solution by given analytical methods. We will discuss some of these analytical methods in due course of time. Now, before proceeding further, we try to discuss the classification of the ordinary differential equation, or we say that before looking for a solution or any qualitative properties, we want to know the class or group in which the equation belongs to, right. So, what are these class or groups? Let us define that. There are various ways available to classify the given ordinary differential equation, and some of the commonly used classification are listed as follows. First, based on the dependent variable. Okay. So, what it means that here dependent variables coming in linear manner or non-linear manner, and second classification is based on conditions. So, if initial conditions are given, then we call our problem as initial value problem, or IVP denoted in a short form, or if boundary conditions are given, then we say that our equation is boundary value problem. In short, we are writing BVP. What are these initial and boundary condition? We will come to know. So, we say that we first classify depending on the number of independent variable, that is ordinary differential equation or partial differential equation, and then we try to define further classify in terms of dependent variable or conditions. So, let us consider the first case, that classification depending on the dependent variable. So, here we try to find out what is linear and non-linear differential equation. So, let us consider the equation, this yn equal to gt y dash up to yn minus 1. So, if the relation g is linear in its argument y to yn minus 1. So, it means that look at the variable of g. Here it is variable is t, y and yn minus 1. These are the argument of this g. So, t represent the independent variable. So, we need not to check, we need not to bother about the that g is coming in terms of g is linear with respect to t or not. We need to consider the argument which are dependent variables. So, it means that if g is linear in terms of y to yn minus 1, then we call this equation 3 as linear ordinary differential equation. Otherwise, it is called a non-linear ordinary differential equation. For example, if you look at this first problem, it is y dash plus ky equal to 0. If you look at arguments of what, it is y dash and ky y. So, here y dash is coming linearly, y is also coming linearly. So, we can say that this equation is a linear differential equation. Here k is a real constant. Now, and if you look at this second equation, dy by dt equal to y square, if you look at here, y is not coming in a linear manner. So, we can call this differential equation dy by dt equal to y square. By the way, here I am writing that this is a y and y dash are coming in a linear manner, and here y is not coming in a linear manner. What do you mean by that? We are going to explain. Because here I can say easily that okay, this is a linear differential equation, and here since y is coming in terms of powers of y, so we say that it is a non-linear differential equation. But if you look at this equation y dash plus mod of y equal to 0, it looks that all these y and y dash is coming in a linear manner, but we really it is quite difficult to say whether it is linear or a non-linear ordinary differential equation. So, we need to devise a method by which we can check that okay, the first one is linear one, second one is non-linear one, and third one is whether linear or non-linear one. So, let us devise a method. So, here we consider the following equation. So, let us consider the following differential equation of order 2. We can we can do this process for any kind of differential equation of any order. So, let us for the time being, let us consider the differential equation of order 2. So, we define Ly as the following operator. Here Ly is equal to y double dash plus pty dash plus qty. It is kind of a operator which operate on y and give rise to this RT. So, it means that you put this y, then this will give you the value RT. So, it is an operator. So, this operator is defined like this: Ly equal to y double dash plus pty dash plus qty. Now, if this operator L is linear, we call the differential equation a linear differential equation, otherwise it is a non-linear differential equation. So, how to check that this operator is a linear operator? So, look at this here, the notation Ly suggests that the operator L operates on a function y to give this y double dash plus py dash plus qy as its value. So, it is a kind of an operator defined on the set of all functions where this y is coming, and it gives you another function of t. So, here Ly give rise to y double dash plus pty dash plus qty. So, we can consider that L is a operator from Vk to Vk, and here V is a vector space V defined on this scalar field K. So, let us say that an operator L defined from Vk to Vk is said to be a linear operator on a vector space V defined on a scalar field K if it satisfies the following equality. So, what is this equality? That if L operating on alpha x plus beta y is equal to alpha times Lx plus beta times Ly, and this is true for all xy coming from this vector space V and all alpha beta coming from this scalar field K. So, if it is true for every xy in vector space V and every constant in K, then we say that this L is a linear operator, otherwise it is called as a non-linear operator. So, once we know how to define a linear operator, now with the help of this, let us see what is linear differential equation or non-linear differential equation. So, let us look at the following problems: y dash plus ky equal to 0, where k is a real constant. Second problem is y dash plus aty equal to bt. Here at and bt are continuous function defined on some interval I. Third one is y dash plus mod of y equal to 0, and fourth one is y dash square plus y equal to 0. So, we will do this classification or checking whether it is linear or non-linear. We take one example. Let us take this example: y dash plus mod of y equal to 0, and you look at the working of this example, and similarly you can check the remaining problems. So, to check whether equation this y dash plus mod of y equal to 0 is linear or not, we define Ly as y dash plus mod of y. So, here we consider only that part which is depending on y dash and all. So, here we will consider only that part which is a function which involves the variable y, and just look at Ly is defined as y dash plus mod of y. Now, we want to check whether it is linear or not, and it is defined on the set of all continuously differential functions over the field of real numbers. Then we may easily check that the operator L does not satisfy the condition of linearity. And how we can check? Let us look at here. So, here we have this L, y is defined as y dash plus mod of y, right. So, the condition which we want to check is this, that L alpha x plus beta y is equal to alpha Lx plus beta L of y, that we want to check. So, operator is defined like this. So, it means that L, what is alpha x plus beta y? So, this value is given as alpha x plus beta y derivative plus modulus of alpha x plus beta y, right. And we can write Lx as what? Lx is x dash plus modulus of x. Now, we want to show that this holds. So, we need to look at alpha times Lx plus beta times Ly, and if you look at it is what? it is alpha times x dash plus alpha times mod of x plus beta times y dash plus beta times mod of y. And if you simplify, it is alpha x dash plus beta y dash plus alpha times mod of x plus beta times of mod of y. So, this I can write as alpha x plus beta y derivative plus alpha times mod of x plus beta times mod of y. And we want to show that we need to show whether it is equal to alpha x plus beta y dash plus modulus of alpha x plus beta of y. So, here if you look at this first term is matching, no problem, but if you look at this term may not be equal. This can be equal only when this x and y both are positive, but this may not be necessary because y is an unknown function. It may be positive, it may not be positive. So, it means that here we see that this is not always true, that alpha Lx plus beta Ly is equal to L time L of alpha x plus beta y. So, we can say that these two are not matching, right. So, it means that here this LHS is not equal to RHS. So, we can say that this operator L, which is defined like this, is not a linear operator. So, we can say that this L does not satisfy the condition of linearity, and hence the differential equation y dash plus mod of y equal to 0 is a nonlinear ordinary differential equation. So, here we have done for y dash plus mod of y equal to 0, you can check others also. For example, here also you can check in a similar manner. You define L here in this case, you can define L of y as y dash square plus y. So, you can easily check that alpha of alpha x plus beta y is not coming out to be alpha times Lx plus beta times Ly, right. So, we can say that here from this observation we can say that this 3 and 4 are nonlinear ordinary differential equation, but 1 and 2 are linear differential equation. So, we have discussed the classification based on dependent variable, and here we have checked that the 1 and 2 are linear differential equation, while this 3 and 4 are nonlinear ordinary differential equation. Why this classification is important and why we have discussed this classification? The reason behind this classification is that the finding the explicit solution of nonlinear differential equation. These nonlinear differential equation are usually very difficult, if it is not impossible. Many times it is very difficult to find out the solution in explicit form. So, we need to know before proceeding further whether we are dealing with linear problem or a nonlinear problem. And there are several methods are available for solving linear differential equation, but no such general methods are available for solving nonlinear differential equation. So, given a nonlinear differential equation, we have to deal according to the nonlinearity present in the ordinary differential equation. But in case of ordinary differential linear ordinary differential equation, we have several methods available, and we will try to discuss some of them. So, therefore, in the case of nonlinear differential equation, the method which provide the approximation solution or qualitative properties are very useful, because we are not able to find out all the times the exact solution of nonlinear differential equation and nonlinear ordinary differential equation. In that case, we try to discuss some other method, for example, approximation solution or the qualitative properties we want to know. Rather than finding the exact solution, we try to find out the qualitative properties of the solution of the ordinary differential equation. So, here we stop, and in today's lecture what we have seen is that what is differential equation, how we can classify of differential equation in terms of independent variables, number of independent variables, and depending on the functions, dependent function involved in the differential equation. So, thank you for listening us. Thank you.